Well, guys, here we are. We're going to take a look at the equation of a hyperbola. Okay? Now, just like the ellipse, just like the circle, the hyperbola is easiest to define in terms of the parametrics. So the parametric equations defining a hyperbola are as you see here. The x and y terms can be defined as products of a secant times of t and y equals b tangent of t, or vice versa. Now, of course, that's defined parametrically, t being the parameter. In our case, the parameter t is an angle. Okay, eliminating the parameter, which would be to isolate the secant and tangent terms, as we can see down here, squaring both sides as we do here. We're going to get x over a squared, quantity squared equals tangent squared, and y over b, quantity squared equals secant squared. And then we can see if we take x squared minus x squared over a squared minus the y squared term, then it's the same as the tangent squared minus the secant squared. And we'll recall our Pythagorean identity stating that 1 plus the tangent squared is the secant squared. And we can come and substitute that up in here in this equation. And lo and behold, we get the equation of a hyperbola as x squared over a squared minus y squared over b squared, okay, equals 1. So we start out with the set of parametric equations defining the hyperbola, and we end up with a single rectangular equation down here defining the hyperbola. Now, okay, the graph is going to look like this, and we're going to come and talk about the derivation of that graph using the distance formula, which you'll after seeing that, you'll be thankful that the derivation by means of the parametrics actually is quite a bit easier. Okay, but the definition of a hyperbola is a set of all points such that the difference between any point and one fixed point and the same point and another fixed point is always a constant. So we're going to illustrate this here and go to the sketchpad offering from which it came. So what we're going to say here is, okay, let's go to the sketchpad. So B is any point on my hyperbola. B is any point on my hyperbola. And what we do is we measure the distance from B to one foci and from B to the other foci, and we subtract their differences, and their differences will always be the same value. Okay, as you can see over here, I've defined this parametrically, and of course this is the secant because it's one over the cosine. So I've defined my graph here parametrically. All right, the distance from B to F1 is computed right here, and subject to change, of course, and the distance from B to F2 is computed right here, and it's subject to change, and we're going to subtract them. And when subtracting them, we're going to see that that is a constant value of 6. Now, you should ask, well, why is that always 6 and not something else? Well, let's take a look, okay? Let's look at these individual pieces, okay? Let's look specifically at BF1, okay? Now, what we're going to notice is that BF1, as this gets closer and closer to this vertex point, okay, my value gets closer and closer to 2. And of course, when it's right there, that value is 2, okay? All right, so agreeably then, this distance, BF1 is going to equal to F2A1, the distance from F2 to A1, which appears to be 2 units when we move down to this vertex right here, okay? So that being the case, all right, you can see that if I subtract this distance of BF2, okay, that's the subtracting the distance of that's BF2 distance right now, okay? When I bring it down to A2, BF2 distance is the distance F2, A2. And if I subtract out of that the same distance F2, A1, then that leftover distance is A1 to A2, which is 6 units. Okay, so that constant difference between any point on the hyperbola and the foci is going to equal this distance of A1, A2, or the distance between the vertices, okay, which is going to be, as measured up here, twice that 3 value, or 6, okay? So going back to our derivation back here, we're going to say that that constant difference, K, is now going to be defined as 2A, okay? So by that's our definition here, where K can be shown to be equal to the distance from A1 to A2, which is going to be 2A. So on that basis, we're going to come and we're going to go through our derivation of the equation of a hyperbola. So here's the same thing right here, all locked up nice and pretty, okay? Here's the same argument over here, that distance is a constant. Setting up our distance formula between our general point xy and the point at F1. Of course, the point at F1 is the point with coordinates. We're, for convenience, putting this on the x-axis. So that coordinates of the focus of 1 are at negative c comma 0, and that at focus over here is at c comma 0. So we're defining the point, the difference between x1 and negative c comma 0 and xy and positive c comma 0. So we write our distance formula down here. We say that it's equal to a constant. We have since argued that that constant is twice a, and that the procedure from here on out is going to be much the same procedure as we did with the ellipse. Of course, with the ellipse, what we found was that the sum of these two distances was equal to that constant 2a. So here we're looking at the difference of those two differences. Okay, so here we account for sign changes and the y coordinate of 0 for the foci point, so it comes down to this, okay? We're going to isolate our radical terms, 1 per side. We're going to square both sides, okay? We're going to square both sides. This is going to square as a and eliminate the radical moving from here to here. Squaring this means squaring that as a binomial, producing a trinomial with still a remaining radical term. So we isolate that radical term and we're down to this point. Of course, we know what we're after. Okay, we've seen the original equation up here, back up here. This is what we're after. Okay, this is where we've gotten to this point, so we continue with that line of reasoning there. Okay, do some algebra. It's a good practice. I'd never ask you to generate this on a test, mind you, but it's a good thing to know. And if you really want to get an algebraic workout, this is the way to go. Okay, so here, with it all said and done, we come down and we generate the equation of the hyperbola as stated here, and having gone through that, you might appreciate that it was actually a whole lot easier to come up with the equation for the hyperbola down here based on its parametrics. So parametrics seem to take out a whole lot of algebra as illustrated on these 2 pages. Okay, so that's some of the theory behind it. We'll come into more applications in the next video.